So today is the 4th of October, 2011, the day that hopefully the Tigers clinched the division series, the day that supposedly the iPhone 5 will be announced, and the day that we're going to cover section 3.1. All right, describing relationships, scatter plots, and correlation. All right, so we've got two sections in this chapter. First one, we're going to look at scatter plots, which we looked at briefly yesterday, which is the idea that we're going to take two quantitative variables and try to see if there's a relationship between those variables. We will talk about those, being able to measure the quality of the relationship between those variables by using a scatter plot, looking at it visually, and also by looking at a quantitative measurement of the quality of that relationship called the correlation. In section 3.2, we'll be looking at something called the least squares regression, which is a way of trying to find the line of best fit. But let's start with 3.1, scatter plots and correlation. Okay, in this section, we will talk about trying to identify explanatory response variables. We've talked a lot about variables. We're going to try to get some new labels put on variables. We will construct scatter plots, and we'll talk about the qualities of a good scatter plot and how we can use those scatter plots to identify relationships. Okay, we'll try to interpret scatter plots. In other words, we're going to try to find some adjectives to describe the relationships between two quantitative variables. We'll look at linear association using something called a correlation, and we'll talk about interpreting correlations. Again, whenever we see the word interpret, we're going to be talking about what words can we push into a situation to describe a relationship, or just describe something that's going on having to do with statistics. Okay, in the same way that you may have to interpret percentile. Oh, there's the word percentile. There's a number that goes with percentile. What does it mean? What are the words that go along with those ideas? All right, let's get started. Can you tell that I had an extra bit of coffee this morning? I feel like I'm... So between the sleep deprivation and the additional caffeine, this is going to be an interesting mixture. All right, so let's first of all talk about the situation that we're in. If I go all the way back to chapter 1, we have data sets. Data sets consist of individuals. For each individual, we have variables that we can measure. Nate Davis, for example, he's got height, he's got weight. Okay, he's got IQ, he's got GPA, he's got an ACT score. He's got brown hair, he's got green eyes? Hazel. Ooh. All right? There's all these things about this individual in this data set that I can measure. Right? Some of those variables are quantitative. Hair color, eye color. Some of them are categorical. Hair color, eye color. Some of them are quantitative. Things that I can use a number with. Height, weight, IQ, GPA, ACT score. Question. If I peel off two quantitative variables, do they have a relationship to each other? In yesterday's opening salvo, we had something like, hey, is there a relationship between hand size and height? And we saw, through making the scatter plot, that we thought there was a relationship between those two things. Well, when we have two quantitative variables, we may want to look at a relationship between those variables that's called explanatory and response. All right? The response variable measures the outcome of a study. The explanatory variable may help explain or influence the change in the response variable. So let's take two variables for instance. The number of hours you study each night and your GPA. Both of them are quantitative. Both of them are described using numbers. Do we think there's a response explanatory relationship between those two variables? And if so, which one's the response and which one's the explanatory? This is where you guys can chime in. If hours of study is one quantitative variable, and GPA is another one. Is there a relationship between the two? Do we think the two
Hours of study will help you get a better GPA.
Okay, hours of study help you get a better GPA. So we're going to declare the hours of study to be the explanatory variable. And we're going to say the response variable, GPA, responds to those hours of study. Seem reasonable? Okay, let's take another classic relationship. Height and weight. Both of them are quantitative. Do we think there's an explanatory response relationship between those two? Yeah. What is that relationship?
The higher or the taller you are.
The taller you are,
The more you weigh.
the more you weigh. Does that seem reasonable? We say that the height helps explain the weight. Okay, that seems reasonable. By the way, CC Sabathia last night,
A lot of weight.
a lot of weight. You know how tall he is? He's 6'8" and 290 pounds. 290 pounds. Holy moly. Okay. Okay. All right. So in many studies where we clearly think there's a relationship to our studying to GPA, where we clearly think there's a relationship between height and weight, many studies are actually designed to say, are these two ideas linked? And when they study them, they don't know whether that link exists or not. Number of cigarettes that you smoke with occurrence of cancer, for example. Exposure to ultraviolet rays with occurrence of cancer, for instance. Exposure to asbestos and cancer. These are, life and death issues. Oh, how about taking aspirin and having heart attacks? No, actually, there's a famous study in the late 80s, early 90s, which actually said the opposite. A small dosage of aspirin every day will help reduce the chance of heart attacks. Yeah, and baby aspirin is often the stuff. I end up taking this, it's a aspirin, it's about 77 milligrams every day. What's that? Good to know. Okay, but we needed to show that the relationship exists. We needed to show that the explanatory variable aspirin helps explain heart attacks. Okay? So, now, in many studies, the goal is to show that there is one or more explanatory variables that cause the change in the response variable. However, other explanatory response relationships don't involve a direct causation. Now, we're going to try to make a real good, big distinction here, and it's going to be summarized with the expression, correlation is not causation. Yeah, more about that in a little bit. Okay, let's just talk about finding out, is there a relationship first? Well, when we have two quantitative variables, we try to visualize the relationship between those variables by doing a scatter plot. Okay? Scatter plot shows the relationship between two quantitative variables measured for the same individuals. So, if I want to find the relationship between height and weight, Nate's one of my individuals. He's going to give me a pair of numbers. He's going to give me his height, 6 feet even, so 72 inches, let's say. He's going to give me his weight, 215, and that is a pair of numbers that I'll plot for that individual. Every single individual, like we did yesterday, gets 1 point on the plot. Now, when we believe that there is an explanatory response relationship between the two variables, we tend to put the explanatory variable on the x-axis, on the horizontal axis, and we tend to put the response variable on the vertical axis, the y-axis. All right? And how do we make that scatter plot again? decide which variable we're going to put on which axis. If there's a clear explanatory variable, again, put it on the horizontal. If there's not one, oh, how about that? The explanatory goes on the x-axis. How clever of them. Okay, remember that you need to label and scale the axes. Okay, by the way, the place where the axes cross does not have to be 0, 0. Okay, in fact, what I want you to do when you make your axis like we did yesterday, I want you to choose a range of values for each axis that spread the data. I think we had the smallest hand that we had in our data set was 15 centimeters. Is that you?
Yeah.
You have a really small hand, Sam?
Yeah.
Okay. And the largest hand was what, 20? 20.5. Okay. Taylor, big hands. Okay. And so what we chose is that scale from essentially 15 to 21 as our horizontal scale. Right? We take our smallest, our shortest person. Who's our shortest person yesterday? And how tall? 4'11". And so that would be at the bottom of our vertical scale. And then who's the tallest? Paul, are you the tallest? Mike?
Danny. I'm thinking Danny.
Oh, Danny. How did I overlook you? And how tall are you? 6'2". What's it like being 6'2"? Yeah. I always wanted to be tall.
If I was 6'2", I'd be in the league.
All right. So anyway, so we choose the range of values from 5'11" to 6'2" on that other axis. We don't start at 0, 0. We spread the data. We choose a range on our axes that fit our data. Just a little bit below. So 4'11", maybe a little. We go to 4'10". 6'2", maybe we go to 6'3" on our axis scale. But we get the data to spread throughout the axis. All right. Make sure to, again, label the axis. Oh, this is the height axis. This is the hand axis. All right? And then, again, plot every individual data point. Okay, go to the next slide. All right. Okay. So, here's, again, a classic relationship. In this case, body weight to backpack weight. Actually, probably backpack weight to number of AP classes is probably a combination of quantitative variables that would also have a relationship. On a side note, by the end of your college days, you are not going to be carrying textbooks.
That's good to know.
And $79 Kindle got introduced last week. Textbook rentals have been getting more and more popular. You are going to be not carrying textbooks by the end of your college days. Say that, Tim. Well, I mean, the cost of the technology is getting low enough that it's not going to make sense to carry textbooks. So by the end of your college days, your backs will be saved. All right, but anyway, so here's two.
I don't see how those two make any correlation to each other.
Well, in terms of hiking and backpacking, people who are heavier tend to be able to carry heavier backpacks. This isn't school backpacks. This is camping backpacks. All right. So if we take our body weight as a predictor as our explanatory variable, and our backpack weight as our response variable, you see how we went from 100 to 190? Why? Because the lowest number here is 103, so let's go a little bit below it. Our highest number here is 187, so let's go a little bit above it for our scale. In terms of the backpack weight, what was our lowest one? 24? Okay, so let's go a little bit below 24. Our highest one is 35, so let's go a little bit above 35. So let's get the data to spread through those axes. All right? And then for each individual, plot the data. All right? And then why do we do this? So that we can interpret that graph. Do we think there's a relationship here? As the people get heavier, their backpacks tend to also get heavier.
What's that little box?
Well, they're basically saying, hey, for the combination of 120 and 26, 120, that data point is showing up there. They're just showing that going up from the horizontal and over from the vertical axis to get that one data point. We're good? All right. Let's move on. I think you know how to make... You've been doing scatter plots for a while, right? A couple days. I think you've been doing it for longer than that. All right. So, interpreting scatter plots. What are the words that are going to go along with those scatter plots? Okay, we look for patterns, and then we look for departure from patterns. Of course, what do we call a departure from a pattern? An outlier. You know, someone who's really heavy who carries a really light backpack would probably be an outlier. Someone who's really light but carries a very heavy backpack would probably be a departure from that pattern. Okay, so here are the things that I want you to look at when you try to describe a relationship that you see in the pattern. Okay, look for departures. Are some of these points not like the other? Call them outliers. All right? And then for the general relationship, we're looking for direction, form, and strength. We're going to look for, just like we had socks, the 4 things you have to look for when you look at a distribution. Socks was shape, outliers, center, and spread. When you're interpreting a scatter plot, I'm looking for form, direction, and strength. Form, direction, and strength. Let's talk about each of those individually. Direction. Typically what we're talking about there, is there a positive relationship or a negative relationship? What's a positive relationship? As one gets bigger, the other one gets bigger. As I get heavier, I carry a heavier backpack. As I get taller, I get heavier. As I study more, my GPA goes higher. Those are all values. All those are showing a direction of the relationship, a positive direction. What would be a negative direction?
You study more, your GPA is low.
We don't expect that to happen, do we, Jason?
No, but it might.
Okay, it might. Well, let's see. What would the things that have inverse or negative relationships? Classic one. As a team's ERA gets higher, their number of wins gets lower. Team ERA is a measurement of the quality of pitching. High ERAs mean bad pitching. Okay, that's a negative relationship. As ERA gets bigger, number of wins goes down. Any other ones that come to mind? As your average speed increases, the number of tickets you get. No, that would be a positive relationship. Sorry.
Well, decreases, the cops can't catch you.
Okay, well, let's...
I'm done with speed and safety.
Okay. Form. Let's talk about form for a second. Okay. Form, our most typical form is going to be that the relationship is linear. But relationships can also be parabolic. They can be exponential. Okay. Form is what kind of shape does the relationship follow? And then lastly, the strength is how quickly or how strongly does it conform to that relationship. Okay? So here's a scatter plot. I'll put some axes on here. Here's another scatter plot. Okay? All right? There's 2 scatter plots. Both of them are positive. Both of them I call it linear. One is a very strong relationship. One is a weak relationship. Okay? So they can be the same in direction and form, but their strength can give two different viewpoints. Okay? So whenever you look at a relationship in scatter plot, we're looking for direction, form, and strength. And then of course, outliers. Are there any points that depart from the rest of the data set. Are we okay with all those ideas? Yes, yes, thank you. I'm trying to think, can we create a word? Doffs? Can we create a word with those 4 letters so that you can remember them? Soft. Okay. All right. So let's go on.
Why don't you just like create one of those things like sad dog.
Almost there, Jason.
Sad dog finds owner.
Oh, ready? Ready for dogs. Dogs often fart stinkily.
I like that. Sad dog finds owner.
Sad dogs
Finds owner.
find owners. What are their owners doing that they when they find them they're sad?
Sad dogs find owner.
Okay.
Dogs are sad because they're lost.
Ah, because they're lost and they found their owner. All right. So use. Hello, Mr. Blanchard. Who's going to be the happy person here? Who wins the lottery? Brad Zucker. There you go. Hey, right. All right. So direction. Direction.
Positive.
Positive. Great. Form. Linear. Strength. Moderate. Let's call it moderate. Our choices are strong, moderate, or weak. Okay, outliers.
Might be that one at the end.
This one here, maybe. It looks like these sort of have this general linear pattern, and this one looks like kind of off. Agreed? Okay, so direction, form, strength, outliers. All right. So there's the general form. There's a moderately strong positive linear relationship here. And again, we think that that one over there may be an outlier. Got the idea? Great. So moderate, long, strong is the strength, positive is the direction, linear is the form. And that's a possible outlier. You guys already know this. You guys are so smart. You're welcome. All right. Now, okay, 2 variables have a positive association. Here's our official definition. When the above average values when above average values in one variable tend to lead to above average values in the other variable. And that below average values in one tend to lead to below average values in the other variable. Okay. Let me draw a picture of that. I'll call this X bar. I'll call this Y bar. Okay? And what we're saying is when there's a positive relationship, we tend to have things in this area and things in that area. Double above and double below. The tendency is towards that combination. What about a negative association? Again, we have an average of our x's. We have average in our y's. And what do we say? If there's a negative relationship, there tends to be above average in one while below average in the other. If I'm above average in x's, I'm here. And if I'm below average in y's, I'm here. So essentially we're saying we're going to be down in this area. And when I'm below average in my x's, I'm above average in my y's. I'm going to be in this area. Do you see that sort of a negative relationship there?
Yes.
Okay, that's what we're talking about in terms of giving the tag, the adjective positive association or negative association. We got that down? Can I go to the next slide? Is there anyone who requires more time? No? All right, great. Let's go to the next one. Oops. Excuse me. Let me get rid of my drawing. Close drawing. Okay. So what do you see there?
Negative.
Negative association says Jason Taylor. Perry, you agree? Jessica, do you agree? Sure. Okay. And if I had to say, average X is about here, average Y is about there, do you see more in those two quadrants? Yeah. Negative relationship. Okay. Linear? Linear? I'm trying to get to the form question. Is it linear or not?
No.
If it is linear, it's a very weak,
Linear. No.
maybe a weak linear, if it's linear at all. Okay. All right. Any departures?
Yeah, that's
Like there? All right. Okay.
That's curve.
Well, and that's why Cody's probably saying he doesn't think it's linear. Right? He sees a curve in that relationship. All right. So they're going to say okay, I said if it's a linear relationship, it's weak. They're going to say it's a curve relationship. If you think of it as a curve relationship, it's a pretty strong curve relationship. All right. And there's this pattern. There seems to be a big cluster here and a big cluster there. Okay. What is this data, by the way? Yeah, it's curved. Yeah, right. Because if form is curved, and that relationship, because we said it's going from here to here, that would be a negative relationship. Have a cluster in the above average, below average camp here, and a cluster here in the below average, above average camp over here. Would you agree with that, Danny? Okay, so it's curved and it's a negative relationship. Okay, let me just explain the data for a second. This is real data, and this real data is responding to this question. Okay, you have a state, and in each state there's a percentage of the people of the graduate high school seniors who take the SAT. Some states, almost every high school senior takes the SAT. Right? Our state, the proportion of people who take the SAT is actually pretty small, isn't it? Say that one more time, Abby.
State colleges here don't require it.
Because the state colleges don't require it, not to mention everyone in this room got to take the ACT for free. Is that correct? During your junior year? No?
Yeah.
Because you're forced to. All right? All right. Now, on this other axis is the average SAT math score for that state. And what we find is in the states where very few of the students took it, they ended up having higher SAT math scores. Down here, where the vast majority of the high school seniors took the SAT, the scores are lower. Why is that?
only the smart people take it.
Bingo. Say it one more time loud.
Only the smart people take it.
Kyle's got it exactly right. Only the smart people end up taking the SAT in the states where it's not required. Why? How many of you took the SAT? SAT, not ACT, SAT.
Oh, no.
Okay? Why did you take the SAT?
My dad made me.
Why did he make you?
He just wanted me to take it for college.
Okay. Here's the reason why. If
Only smart people can take that.
what? But why is that?
Because they probably don't. Isn't the SAT you gotta take before go out of state, right?
Well, there's a lot of colleges, especially in the East Coast, that only take the SAT. So if you're applying to any of the Ivies,
Yeah, you gotta take
you got to take the SAT.
only smart people.
Well, the tendency is that only if you have ambitions to leave the state for college do you tend to take the SAT. And people who do that tend to only be those who are interested in paying more expensive tuition. If you leave the state, things get automatically more expensive for you. Not only in terms of tuition, because you have to pay out-of-state tuition or private school. Your travel costs are higher.
Wake up, guys.
I should be him. I'm the one who should be out right now.
Maybe she was at the
Maybe
You,
you take a game, too.
Andrew, were you at the game? Did you stay up and watch the game? No. You got a lot of homework? Okay. Sorry. I'm working on 4 hours, so, but I got the coffee. Oof. All right. So let's go on. Let's just go back to this one idea, though. Okay, we use these words to describe the relationship between the two variables, and then we use these words to describe the relationship between the two variables, and then we try to find the story behind the data. The scatter plot shows us something, and then behind that something there's a story. Only people who have ambitions to go out of state take the SAT. That's the story behind the data. Okay? All right. Okay. Now, these ideas, linear for form, for example. These ideas, moderately strong, strong, weak, to describe strength. All of those things, we were just looking at the dots and then making up those words. What I'd like to do is to spend a few seconds talking about this idea. Can we quantify any of this? Meaning, can I take this I think or I feel or I believe it's linear? I think or I believe or I interpret this as strong. Can we take any of those things from feelings and gut reactions? Can we change it into this number tells me something? Can we quantify the relationship between the two variables?
I'm sure there's a way.
Otherwise, why am I talking this way? All right, it's a teaser.
The correlation.
Okay, and it's called the correlation. Indeed. So, our definition for correlation is a number, and we're going to use the letter R to describe the correlation. It measures the strength only of linear relationships. Right? It measures the quality of the strength of the linear relationship of two variables. Right? First of all, let's talk about the kinds of values that R takes on. It can only take on the values between -1 and +1. We say if the R value of 1, it's a perfect positive relationship. A perfect positive relationship between two quantitative variables could be things like, hey, I got a job, I make $8 an hour. I work 1 hour, I make $8. I work 2 hours, I get $16. If I work for 3 hours, I get $24. That relationship is perfectly linear. That data would have an R value of exactly +1. If it's a perfect negative relationship, the R value has a value of -1. Any value, though, of R that's greater than 0, we'll call a positive association. Any value of R greater than 0 tells us that the relationship is positive. And likewise, any value of R less than 0 tells us that the relationship is a negative relationship. And if the values of r are very close to 0, it might suggest there's actually no relationship between the variables. For example, in baseball, there's probably very little relationship between your uniform number and your batting average. They're both quantitative variables, but there's probably little relationship between your batting average and your uniform number. The strength of the linear relationship increases as r moves away from 0 and toward either -1 or +1. The closer you are to 1, the closer you are to -1, the stronger the strength of the relationship. The closer you are to 0, the weaker the relationship. We good on that idea? So now, instead of just saying, I think that's a weak relationship, or I think that's a strong relationship, we now have a value to look at, and then we can interpret that value. Does anyone require more time on this slide? We're good? All right. Okay, actually, well, and I already said this. The last point was, indeed, values of -1 and +1 are called perfect relationships. Perfectly linear relationships. Okay, go right to the next slide. All right. Here's some examples. In example number 1, is there any clear relationship? No. Oh, look at the R value is 0 in that particular set. Do you see a slight negative relationship there? Oh, it seems to be a negative relationship, but it's a pretty weak one. Oh, the R value is -0.3, relatively close to 0, and it's negative. Over here, the relationship is strengthened and it seems to be positive. The R value is 0.5. Let's call that a moderately strong positive relationship. How about this one? Oh, looks like the relationship is strengthening, but it's not perfect. They don't line up exactly in a line. That looks like a moderately strong negative relationship. Oh, but look at that one. We're going to call that a strong positive relationship with an R value of 0.9. And that one, nearly perfect. Nearly perfect. Its R value, very close to -1. A strong linear negative relationship. All right. The formula for R is complex. But it's important that I show it to you. All right? It's important that I show it to you because there's some restrictions on when we can use it. Are you ready? First of all, we've got a data set that are made up of a bunch of x's and y's. And those x's and y's are always in pairs. x1, y1, x2, y2, x3, y3. We have all those pairs. All right? All of the x's values have an x bar, the average of all the x. All the y values in their pairs have an average of them. Call it y bar. All right? When we have all those x, y pairs, and again, think about the values of x bar and y bar. Oh, by the way, all those x's have a standard deviation. All those y values have a standard deviation. Let's call those standard deviations S sub x for standard deviation of x, and S sub y for the standard deviation of y. We pull all those things together, and there's what the calculator is doing for you when they calculate the R value. Do not write this down. All right? But let's talk about the pieces of it. Okay, first of all, look at this pair, this product. It says take an x value, subtract it by its mean, and divide it by its standard deviation. Wait, take an x value, subtract it by its mean, then divide it by the standard deviation. It's a z-score. Okay, and then multiply that by, take a y value, subtract it by the mean of the y values, and divide it by its standard deviation. Another z value. Now let's think about what happens when I have an above average x value. What kind of z values come out of that? Positive. What if I had an above average y value? I get another positive value. What happens when I multiply two positive values together? I get a positive value. Okay, change gears. What if I have a below average x value? I get a negative z value? Sorry, negative z value? What if I have a below average y value? I get a negative z value out of that. What happens when I multiply two negative z values? They become positive. Okay, so when we have a positive relationship, this product is either going to be double positive or double negative. Regardless of whether it's double positive or double negative, the net result is a big whopping positive. And if I had a bunch of those positive products, I end up getting a positive sum for all our data. Oh, when we have a positive relationship, we are either in this corner or this corner, right? Double negative or double positive. You can see why this particular formula produces a positive value when the data has a positive relationship. Okay, let's play the other game. The other game. What if there's a negative relationship? What's happening here up on my elbow? This is, by the way, where I fell down the stairs. That really hurt when I did that. He's laughing at my pain, Andrew. Ruthless. No heart. I got no heart. All right, so I'm up here. I've got a negative relationship. Hey, my x's are below average, but my y values are above average. My x's are below average. What kind of z values do I get? If I have a below average x value, what kind of z value do I get out of that situation? A negative z value. When I'm up here on the corner, when I'm up here in the, those y values are above average. What kind of z values are coming out of them? Positive. Hey, what happens when I multiply a negative by a positive? I get a negative value. Okay, what about down here at my fist? Positive x value. I'm above average on the x scale, but I'm below average on the y scale. I'm above average on the x scale, but below average on the y scale. And again, it's a negative times a positive. The overall result here is a big negative. And what happens if I sum up a bunch of negative values? I get a big old negative value. So when there's a negative relationship, this formula will clearly give us a negative value. So that's why you had to look at, you don't have to do this ever by hand, but you have to have the insight of how it's doing its work. Here's the last thing that we have to say about this formula. This formula uses an averages of the x. This formula uses averages of the y. Averages, means, are not particularly good measurements in some circumstances. I'll say that again. X bar and Y bar, the mean of X and the mean of, are not good measurements in some circumstances, and I've been trying to hit this point again and again and again. Under what circumstances are means not good? Not at curves. Outliers. In the presence of outliers, means are not good measurements. Wait, that means if we find ourselves in a relationship, a scatter plot that has outliers, the R value is going to be screwy. It's not going to be a good measurement. In the presence of outliers, the R value may not be a legitimate measurement of strength. In the same way that in the presence of outliers, any mean may not be a good measurement of central tendency. So watch out for that. All right. I'm ready to go to the next thing, I think. Okay, so facts about correlation. First fact. The value of R measures the strength of a linear relationship. It does not measure how well one thing causes the other thing. All right? Say that one more time. It's so important. I'm going to ask even Miss Munoz to sit up and pay attention. Ready? The value of R does not measure the quality of the causal relationship. It doesn't measure how well X causes Y. It doesn't know about causal relationships. I take all your height data and I put it in my X data. I take all your weight data, I put it in your Y data. I run a correlation and I get an R value of 0.7. Does that mean height caused weight? Know why? Because if I switch them around, if I change the X and Y's, if I put the height data first and the weight, if I put the weight data first and the height data second, I get the same R value. It does not know causal. It does not know explanatory response. It is not evidence to a causal relationship. R does not change if we reverse the X's and make them Y's and make the Y's X's. Summarized by this line. Correlation is not causation. One more time. Correlation is not causation. A high R value does not prove that X caused Y. The formula doesn't know causal relationships. Item number 2. R does not change when the units of measurement of, if you change the units of measurement of X or Y, or both. Okay, what does that mean? I'm a European. I'm doing study on climate change. I'm looking at the relationship between temperature and rainfall. My temperature is measured in degrees Celsius. My rainfall is measured in centimeters. I find an R value. I change all that temperature data into degrees Fahrenheit. I change all that rainfall data into inches. I run the analysis again. I know it. I get exactly the same R value. When I change my units, it does not change the R value. R itself has no units. It's a unitless measure. Okay, I think, at least in prior years, we had questions on the test that read something like, which of these statements is wrong? And one of them was like, the R value is 0.5 meters per second. And you see the presence of a unit as a reason why that R value of that statement is false. Other ways that R values could be false. Hey, the R value is 1.5. That also breaks a rule. All right. So cautions. Both variables need to be quantitative. Correlation does not describe the strength of curve relationships. Correlation is not resistant to the presence of outliers. I see by the way you're packing up, I must have very little time left.
You got like
2 minutes. All right. All right. So we've only got, I think, this last slide to go, and then you're going to be ready to go for your homework. Take a look at this relationship, please. X-axis is the number of boats registered in Florida in the thousands. On the y-axis is the number of manatees that were killed by boats.
the more boats, the more killed men.
Okay, tell me about that happy dog.
The more boats, the more killed men.
Okay, no, okay. The more boats, the more killed manatees. But I want direction, form, linear, strength, strong. And are there any outliers? Not really. Okay, how about that one? No, sit down. I got you to the bell. I'm taking you all the way to the bell. How about that one? Weak? Weak? If there is a relationship, it's a slight positive relationship. And know what I think? I think that's an outlier. All right. tomorrow for quiz 2-1. I gotta stop the recording first.